So remember that in the last video, we were talking about if a graph has an induced subgraph, that's a complete graph on some m number of vertices. We're going to define that as an m-clique. So an m-clique in a graph G is just an induced subgraph of the graph that's isomorphic to a complete graph, right? So it's just some selection of the vertices of G and then all the edges between them, so that that induced subgraph happens to form a complete graph. We call the clique number, which we denote omega of G, it looks like a W, but that's a Greek letter omega. The clique number omega of G is the order of the largest m-clique in a graph. Okay, so just as an example, if your graph is this, right? The clique number is the size of the largest m-clique. So the largest induced subgraph that is a complete graph. Okay, well let's think about what the complete graphs look like in general. K2, this is sort of an aside, a little bit of scratch work here. K2 just looks like two vertices and a single edge between them. K3 is three vertices and all edges between them. It looks like a triangle. All right, we certainly have an induced subgraph, that's an edge. We have an induced subgraph, that's a triangle. K4 is four vertices and all possible edges between them. It looks like a box with an X through it. And yep, we do have one of those here. K5 looks like sort of a pentagram with a pentagon around it, this thing. We don't have any of these. So you can go ahead and check, but there's not really enough vertices of degree 4 for us to have a K5 embedded in here, right? We don't have enough vertices of high enough degree to have a K5 as a subgraph, which means the clique number of this graph, the order of the largest m-clique in this graph, is 4, right? It's this subgraph right here. Right, we don't have a K5, our largest K-clique within this graph is K4, and so the clique number is 4. And what we had seen in the last video is that, well, I know that these 4 vertices just on their own are guaranteed to need their own 4 colors in a proper coloring. Remember, proper coloring means any 2 vertices that are connected by an edge have to have different colors. And so these 4 vertices, because they are complete amongst themselves, they all need their own separate color. And so we can conclude that we're going to need at least 4 colors to have a proper coloring of this graph. Right? More formally, the lower bound theorem says in a graph G, omega of G, the clique number of G, is less than or equal to the chromatic number of G. In other words, if your graph has an m-clique, you need at least m colors for a proper coloring. Okay, right, it's not telling you exactly what the chromatic number will be. It's just giving you a lower bound. It's saying you'll need at least this many. You'll need at least 4 here. And in fact, you can color this graph with 4 colors, as you can check. But that's not necessarily always going to be the case. This is a less than or equal to, it's not an equal to sign. So proof of this is simple enough. Suppose omega of G is equal to m. That is, G contains Km as an induced subgraph. Well, that means that among those m vertices, we have every possible edge connecting them. So no pair of those vertices can have the same color. Thus, at least omega of g, or m, many colors are needed in a proper coloring. This gives you a starting place, right? And it gives you a way of trying to prove in general that the chromatic number of the graph is a certain thing, because it's saying, well, I know it can't be any less than this. And so if you can prove, for example, that it's possible to do it in that many colors, then you're done, right? In this graph here, the lower bound theorem tells me that since my clique number is 4, I need at least 4 colors. So if I can demonstrate a proper coloring with exactly 4 colors, then I am done. And I can, right? Just color, let's say this is yellow, this is yellow. We'll color this one red. We'll color this one blue, and this one purple, right? This sort of helps me in arguing that the chromatic number is exactly 4, because I can demonstrate that it's possible with 4, and the lower bound theorem tells me it's not going to be any less than 4. Okay, now it doesn't tell me necessarily that that's the case. Sometimes the chromatic number will be strictly larger than that. If the chromatic number is exactly equal to the clique number, if chi of g is equal to omega of g, then we call that graph perfect. So a graph is called perfect if chi of g is equal to omega of g. That is to say, if the clique number is equal to the chromatic number. So this graph here is perfect because its clique number was 4 and its chromatic number was 4. These 3 graphs we did in the last video, also perfect because their clique numbers were 5, 3, and 2 respectively, and their chromatic numbers were 5, 3, and 2. What about this first one that we did? Because we were able to find a 4 coloring here, but I encourage you to play around with it and see if you can find a 4 clique. Pause the video if you want, play around, but you probably can't. Hopefully you can't. I don't think there is one. I don't think there is a 4 clique here. I think in this graph, the clique number is actually 3, but the chromatic number is strictly bigger. It's 4. So why is that the case? Well, here's sort of the issue right here, or one possible issue. We've got this sort of 5 cycle within the graph, going from A to B to D to F to G. And we know from when we talked about bipartite graphs that if you have a 5 cycle, you're going to need at least 3 different colors to color those 5 vertices. If you try to alternate around, you're going to get stuck, right? Red, purple, what? You can't use red or purple again because its neighbors are already red and purple, so you need a 3rd color here. But then in addition to that, you have this extra vertex in the middle that's adjacent to all of these. So you need 3 colors around the outside, and you need an additional color on the inside of this sort of cycle because it's universal within that cycle. It's attached to all 5 of those vertices. So there's no way to actually color this using just 3 colors because we need 3 colors for the 5 cycle, and we need an extra color for that center vertex. Okay, so this is an example of why the lower bound theorem is just that. It's a lower bound. It's not necessarily going to tell you the chromatic number. It's just going to say it's a lower bound. And that's true, right? The clique number here is less than or equal to the chromatic number. So not all graphs are perfect. Okay, so one last thing to sort of tie this up. In that first example that we did in the last video, we were trying to figure out a way to color a map so that any 2 bordering counties had a different color. Well, in graph theory, graphs of this type, maps, always end up getting transferred into a graph that has a special property. We call it a planar graph. So a planar graph is just one that you can draw in the plane, like on a piece of paper, on a whiteboard, or whatever, something flat, that doesn't have any edges crossing, right? We call a graph planar if you can draw it on a plane without any edges crossing. So I've drawn 4 graphs here, all of which have some edges crossing. Some of these are planar, I've just drawn them wrong, right? In particular, K4, I could redraw it like this. I could just sort of pull this vertex down and draw it in the middle instead. And now it's drawn in a way that is planar because no edges cross in the plane. Here we've got all sorts of edge crossings, but maybe I just drew it wrong. I could try to sort of pull this vertex over to the other side maybe and draw it like this instead. Wouldn't be like this. Oh, but see, that's already a problem. I was trying to draw something like this, but we still have a crossing here. Okay, so play around with it a little bit, but this is an example of a graph that's actually not planar. There's no way that you can draw this graph without having edges cross if you're drawing it on a plane, if you're drawing it on a flat surface. K23, it's not drawn in such a way that's planar right now. There's lots of different crossings, but the graph itself is planar. If you just sort of take this vertex and sort of pull it down below, you could redraw this as this. Okay, so this is planar. It's possible to draw this graph in such a way that no edges cross, but K33, again, play around with it a little bit, you'll find that this is not planar. Right, but in particular, any map can be represented as a planar graph. If you take any kind of a map and redraw it as a graph, like we did in that first problem, in the first video, it's going to be a planar graph. And so one of the largest unsolved problems in graph theory for a long time is something that we now call the four-color theorem. The question was, or I guess the conjecture was, that you can take any planar graph and you can color it using exactly, or 4 colors or less. Right? Obviously, some of them you can do in less, but it'll never take more than 4 colors. And it took graph theorists a very long time to solve this. I'm not going to solve it for you here because I couldn't possibly. The way that this 4-color theorem was eventually solved is by computers. And some mathematicians, if they're very pure, will tell you that it doesn't really count because essentially we had sort of a series of supercomputers work on this problem, and by brute force you were able to sort of check off all the various different cases and confirm that any planar graph can be colored using 4 or fewer colors. Which is sort of a crazy thing to say because there's infinitely many planar graphs. How does a computer check this? Well, they had to sort of break it down into different specific cases, and no human could ever really check through the code and make sure that the computer did it correctly. I mean, they could check the code itself, but they couldn't actually, it's too much, right? It was too much for the computer to do to really be able to check and confirm that this is true. So most of us in the math community have accepted this theorem as proof, even though there's not really a nice slick proof that you can really read through logically the way that we're used to reading proofs. So there's some debate over computer proofs. If this is something that interests you, I'd love to talk to you about other different types of proofs that were used using a computer like this. But that's the 4-color theorem. And so it says in general for any graph, or for any map, you can color it using 4 colors or less so that any pair of bordering areas have different colors.